Okay, so we just finished the PCA, and then we will teach about LDA. Usually, PCA and the LDA they link together. They are linked together, linking together. Why? Because PCA is for dimensionality reduction. So our dimension from high dimension, we have big data, and reduce to the low dimension data. And then the purpose is we try to do classification, like a face recognition. Okay, so next step is for discrimination, actually is classification and using the LDA. So linear discrimination function. Okay, so all the method, like at my time, the company I work on, we are the best face recognition company in year around 2000. OK， 我们现在公司全美国最好的人脸辨识公司。So we use the PCA and the LDA, but we have our own LDA method. Right now, the new face recognition method they use deep learning, and so far as I know, the best face recognition algorithm is from China. So China, they are doing very good on this face recognition. Okay, and the method is continue the PCA and LDA idea, but they use deep learning to do that. Okay, so the paper are good. Okay, 所以他们有用这个方式继续延伸到 deep learning， 这大概让你知道一下。Okay, so what's the LDA? So before we talk about LDA and the SVM, one important thing we would like to introduce you is the linear algebra things. Okay, the linear combination, or we call discrimination line. 就你怎么用一条 discrimination line 来区分两边这样子哈。那 SVM supported vector machine, okay, the same. You have two classes, and how can you find this discrimination line to discriminate or to separate the class 1 and class 2, for example? 所以你怎么找这条线找出来？这条线就是 discrimination function 的东西，一条线嘛 ，discrimination function. Okay, so the difference between the LDA and the SVM. SVM is LDA is project to a lower dimension. Okay, SVM is project to higher dimension using kernel function. Kernel function is the activation function. So two are different. Okay, so the deep learning, they also apply activation function for discrimination. Okay, but for face recognition, right now using deep learning, they don't use LDA, but the concept, no matter it's SVM, okay, the same. The concept is the same. Okay. Because deep learning they use activation function, so that means they do project to higher dimension. But however, the discrimination concept, the classification concept is the same. Okay, so here I would like to teach you is that suppose this is a line. Okay, so if this line passes through the 0, 0, so the line equation is this one, W1 x1 plus W2 x2 if it's two dimension. 二维的话 is this one. So W1 and W2 are the coefficients. 它的系数嘛 W1 跟 W2 是它的系数。Okay. And usually we have one more term is a constant term. So the equation is this one, right? Is W1 x1 plus W2 X2 and plus the constant term. So constant term is what's the physical meaning for constant term? Is translation. 位移嘛，constant 是位移，就这条线的位移。那这条线位移是 along the normal direction W. Okay, so this line, okay. So suppose 0, 0 here, this line here, right? And then this is W, and this is L. So if the constant term is 0, that's meaning this line pass through the origin, 穿过原点. If this is not 0, B, that's meaning this line will shift along the W, the normal direction. So they'll shift this way. So the B or the constant B called bias or translation or threshold. W, this is a translation. But in the deepening, the constant term is a bias, called bias or called threshold, because this is equal to 0. Okay. So this is constant and shift along this W. And what's W? W is rotation and scaling. So it's kind of affine transform. So W is rotation. Why W is rotation? W is this one, normal direction. So this is W, this is 9. So the W is this one. If you rotate W, because of the line, they have a normal direction. The normal direction is W. So if you rotate the W, it means this line is rotated. In this case, we don't have a scaling, because scaling is meaning this along this unit vector, they will change the unit vector. Okay, so we fix the unit vector. So in this case, W is only the rotation. Okay, so each line L, they have a normal direction. The normal direction is the rotation factor, and rotation is here. 这样知道哈，一条线是这样哦，好，任意一条线，所以 W 是它的 rotation， 控制它的这条线 rotation。So we write the equation linear algebra, we write the linear combination term， 这是一个 linear combination term 啊，是这个方式。But I always told you the AX equal to B problems. Okay, so when we do the programming, we do the coding, we don't write the equation, we write a vector. So any linear combination can be the vector or matrix. But in this case, it's because it's only one equation. Okay, so this is a one vector is the other vector. If there are more than one equations, and here will become a matrix like A. So AX in this case equal to 0. Constant, because they don't have a constant term. Oh, sorry, they don't. This is just an equation. Okay, so this is we call it, this is definition for this line, and this line is a discrimination line, or because it's a line, it's not a curve, so we call the linear discrimination function, because this is a function G or F. This is a function. Okay, so this is a function, and it's a linear. But if there's a curve, it's non-linear. Okay, so this line is equal to the SVN, this line, the same. Okay, and in one side, this side, class 2 is meaning this result is bigger than 0. In this class 1, result is smaller than 0. That's meaning if you input any point, x1, x2, 那一点是坐标 x1, x2 带进去，那这边的 those points are bigger than 0, and this point is 0, and the result, the equation result was smaller than 0. So that's a discrimination. So the purpose how can we find this line? Okay, so here for the classification, there are two methods. One is a LDA. The other method is SVM. Both methods are important for machine learning. So we back to here. So in this figure, suppose we have two classes. One is the cross mark, 打叉叉. The other is circle, the dot or the circle. And can you find a best discrimination line, this one, to separate both classes? So how can we find the discrimination line? Okay, to separate both classes. If it's 2D or 3D, 2D or 3D, in this example is 2D, x1, x2, 3D is x1, x2, x3. Usually more than 3D, we call this is not a line, it's a plane. 3D is a plane. 3D is a plane. 2D is a line. Okay, but more higher than 3D, we call hyperplanes. 高纬度的 plane 这样子，因为没办法去画这种四个纬度的嘛，所以就 call hyperplane。好 ，so our purpose is to try to find which line we call discrimination line can separate both classes. So that's a LDA. So we have several samples, cross mark and circle. We continue. So in the x is a 2D. Any points is x. Okay. So in order to find this line, actually what we do is that each point we want to project to the W plane. 这个解法是说，你为了找这一条线，基本上就是找到一个 projection 的这个 W is a rotation plane or rotation line. This is what I say. 我们之前这刚好有点相反哈。This L and this W. Okay. So W is always pass through the 0, 0. W 是在这上面，那 L 是这样移动。这个图我想这样画好像比较不好，因为这个刚好相反。这个 L 是在这里 ，W 是在这里 ，W 在这里。那 your class is here, so you will project to the W. So all the point will project to the W. 一样，只是这里啊，这一个 class, this one class, the other class in this example, in this L. So suppose this class is bigger than 0, this class is smaller than 0. So they will project on this W. This one project to W. This one also project to W. Okay. Here is just draw difference. 这个只是画不一样而已。这个 L 反正是这一条线，那 W 是在这里。那这 W you rotate W. So this is L. So you have a rotation and you have translation, shift. This can shift. This is L, this is W. W should pass through the 0, 0, 0. And this L, because it's controlled by the W, so rotation. And this L will do the translation along the W. 这物理意义是这样，这个 L 是会在这里上面移动，那旋转是受 W 控制。所以 this what we try to say is that all the 2D points will project to the W. So here you will find this x1, x2 for each point. So you assume, you find, suppose this look like a Gaussian distribution here. This is the other, the first Gaussian distribution is the X for X. Second Gaussian distribution, we do modeling using Gaussian model, okay, is a circle. Okay, so we will find the mean of 2D, the other mean of 2D, and the standard deviation in 2D. If let's project to this line, you'll find there is the Gaussian distribution in 1D. So the LDA, after you do PCA can reduce the sample dimension from the very high to very low. LDA is only reduced probably from 2 to 1, 3 to 2. Okay, so in this example, each point is 2D, so we project to here. So we'll have the Gaussian distribution here, and the other Gaussian distribution here. 这里没有线可以画，这里不大，这里画能不能画？好，那我们这里就有一个，这有一个Gaussian distribution 这样子，然后另外一个。the other Gaussian distribution， 这个是比较，也是这样子。So from 2D project to 1D. Okay, so our purpose is try to reduce the overlap region here. That's our purpose. So we try to find a line. Use the other color. We try to find a line, and they can be like here. This is our purpose. Our purpose is in 2D, we want to find this L can separate both two classes in 2D. But LDS say we can reduce to the lower dimension, and probably that's easy. So we will project to this 1D. So the Gaussian in higher dimension, or Gaussian distribution in higher dimension, when they project to lower dimension, is still a Gaussian distribution. The Gaussian distribution in higher dimension, they project to the lower dimension, is the distribution is also the Gaussian. Okay, so LDA, the purpose is that we try to reduce the overlap between two. We try to find a line. And this line pass through, they can separate two Gaussian, and then they can read the smallest, the overlap. Okay. So what can they do? So in this is a 2D. Why is it 1D? Here is X, and here is project to Y. Project to Y. So X, we want to project to the W, become Y. That's meaning, for this example, any point, this point, right? Point meaning what? Point meaning a vector. So any point here, there's a vector here, okay? So you have point here. Point meaning what? From 0, they have a vector. To here. And this vector will project to the 1D. Project. So this here is x. Here become projection is y. Okay. So back to here. So x inner product, projection is the inner product. So x project to w will equal to y. So the purpose is try to find w. Okay. So we keep going. And w is a unit vector. The definition for w is a unit vector. So first of all, because in 2D, we try to find, there are two classes. So first one, we will try to find the mean value for each cluster. So we have a M1 and N2. So X is the sample in 2D. So we'll find average value M1 and the M2. Here we try to prove is the mean value in the 2D is equal to the mean value project to the 1D. The same the mean value. What I try to say is if you have an average value here, average value here in 2D, okay, and you do the projection, there's a vector, and you project to the W will be support here. This one project to W will be here. So when you this mean value is based on all x. This the other mean value based on the other circle. This x. Your projection in the y-axis. Here's y-axis. And then actually this is a, we just said this is a Gaussian distribution equal to all the projection y. Sorry, for the equal to the average value for all the projection y. The same, this one you project to the raw dimension. This mean value equal to each x project to the y, and you got the average value. 就是在高纬度，你的平均值的命值等于直接在算低纬度的平均值，一模一样。所以这里要跟你讲是这件事情。So they prove this high dimension, this low dimension, so it's called projection mean. It's meaning in each point in high dimension, you project to W9, W vector. 这个 project 到这里的时候，那等于这个总和嘛，平均，然后这个实际上就是 y， 在这 projection 的上面就是 y 值嘛。那这个 y 值你会发现，因为这是一个常数 ，W 是一个常数项，你把 W 提出来，你会发现，哦，原来你的 projection 的平均值等于高纬度的平均值，直接的那个平均命直接 project 到 W 上面去，为了证明这件事情。So what's our purpose? So our purpose here. Well, this one, we hope when you do the projection in the low dimension, there are two Gaussian distribution. Your purpose is you try to find a W. This W can let this two Gaussian, the distance between two center. We want to find maximum value of this one, maximum value of this one. So the distance between two mean value will be bigger. For each standard deviation will be smaller. Okay, that's meaning we try to find maximum value of this one. 要找极大值，这是 equation。那就是你的 projection 的Gaussian distribution， 你的分子越大越好，你的分母越小越好，这是它的目的。discrimination 是这样子。那这个就是我们提到这里，再继续。 我们再回到这里解释，这个平均值嘛，这个平均 average value, right? So your purpose, you try to find a line here to discriminate both both distribution. And the way we'll do is we project to the lower dimension. So we have lower dimension here. Okay. And the other Gaussian distribution is here. And the average value mean is here. The average value mean is here. So suppose this is M1, this is M2. And you have standard deviation, rho 1. Standard deviation, rho 2. So our purpose is try to find this W projection line, the W, okay? And the W, when they project to this W, the M distance between M1 minus M2, the distance is larger. Larger meaning the two distribution will be far away. You want W1 plus W2. That's meaning individual, each one will be as small as possible. That's meaning this distribution is one. This result is better because the overlap region is small. This is not good because overlap region is too big. Two center, right? So you hope M1 and M2 be as far away as possible. You want the standard deviation smaller. Standard deviation smaller is meaning what? Meaning the distribution is like a narrow, like this one. No, standard deviation smaller is meaning the distribution is smaller, narrow. 这样子. So that's our purpose. Our purpose is this one. So we want to maximize this one. Okay. So what can we do based on this one? Let's just tell you, okay, this is not good. Bigger overlap. This is not good. This is also not good. So back to here. So our purpose is try to find maximal value of this one. Okay. So what's M1 and M2? M1 minus M2 is average projection at mean value minus projection mean value 2 is meaning original X mean value and the mean value and they project do the projection. 我们刚刚讲高纬度的平均值 mean value 上等于在低纬度的 mean value 等于高纬度的 mean value 直接 project 下来就好了，因为 mean 也是一个点嘛，所以在高纬度的平均值，你要求低纬度的平均值，就直接把高纬度平均值把它 project 下来。So that's meaning when you try to find the low dimension average value is mean this one. Low dimension average value is meaning in high dimension average value directly project to the W. So it's the same. So this equation will be this equation. And this equation, the same, will be this one. SB is what we call between two mean value. SB means between mean value. So what's SB? They define SB is here. This is a low dimension M1 minus M2. Okay. I say again. This is original, we call Jacobian, or original format. And this is one also called Fisher linear discrimination. Fisher linear discrimination also called linear discrimination function. 这两个是一样的。那我们的目的就找 W， 那我们要 maxima 这个值，那市场就分母这个要 maxima， 那分子要找大值嘛，那分子的这个 M1 就是 projection 的 M， 那这个 projection M 我们到下一页这边，就这里。那so this one equal to the high dimension M1 minus M2 project to W, but because it's square, so it must be square. Okay, so after this one, because our purpose is try to find W, and mean is given in high dimension, mean is average value in high dimension. So both one and both is we define SB. So the denominator term become this one. 这个 term, this term will become this one. So we know SB. We will try to find W. And SB is this one. SB is the average value in high dimension. So we know this one. Okay. And what's the denominator term? This term. And this term is here. Because, we're back to here. Because this term is a standard deviation square. S is standard deviation square. Okay. So we continue. This is we define S is standard. S they call SW. W what? The within. This is between two center. Within is what? Within is meaning first standard deviation and second standard deviation. So that's within， 就是自己本身自己要 within 自己本身的哈 within。但是 within 就是我们讲到这里。So each S is a standard deviation. Sorry, a variance. The variance. So the denominator we have a variance 1 and variance 2. So we plus together. However, each variance is this one. The same, the higher dimension variance project to the lower dimension variance. So become this one. So SW is the individual variance in higher dimension. So you can find SW. So finally, the equation become this one. So become this one. This is our formulate. 所以我们最后的式子在这里。So original definition is this one. Jacobian this one. Or your function is this one. Finally, from this one, we will transfer, become this format. So we know SW, we know SB. We try to find the best W rotation. So we try to find best projection vector. So if after we find W, and that's our answer. Okay, so we know SB and SW, and we try to find W, the rotation vector. Okay, so we try to do is that we just directly do the derivative. 我们要找 W 嘛，那直接就跟 W 做微分这样子，就这里。所以这个就直接做 W 做微分，就变成这样。And this one, I write the equation here. 你自己在看啊 ，this one here 有分子分母的微分嘛？啊 ，you have a denominator, and we try to derivative x. So the equation here is become v squared, and u derivative u times v minus u times derivative v. This equation here. So after this equation, the derivative equation, okay, the result become this one. And you'll find out this term actually equal to Jacobian. This term equal to this one. And our purpose is try to find maxima value of this one. This is a constant term. So we define this term called lambda. 这是一个常数项，但是我们求这个为什么是常数项？因为分子跟分母是其次，是同样的次，同样是2次，所以就剩下常数项啊。那我们求这个最大值，那这是一个常数项，所以 define this one is a lambda. It's constant. Okay, here, this one. And you will find actually W equal to eigenvector. W equal to eigenvector. So this term become this term. And this term is a eigenvector problem. Why? Because if we shift SW, switch to the other side, will become this one. So that's meaning constant times vector equal to X equal to B problem. The other matrix times W. So W, we can solve this one. Optimize this kind of optimization process. And this process can use singular value decomposition to solve it. Okay. So this one, this is a known. We know this one. And W is the eigenvector, and lambda become eigenvalue. So we directly use the SVD to factorize this one. 我们是因式分解这个 term， 那出来的解，后面好像没有了。出来的解就是会变成 UWVT problems. Okay, so our solution is this one. So this term become A. So use SVD become UWVT problems. In this case, W equal to lambda, eigenvalue, U equal to omega. And we don't care about this term. Okay. Because we try to find maxima value of this one. So that's meaning we try to find maxima value of eigenvalue corresponding to one eigenvector, and this W will be your solution. That's it for the W. That's the answer for W. Okay. And this W, after you do this process, you'll find the W is here. So this W can let each point project to here, and then there's distribution here, and the other distribution here. And the overlap is the smallest. So actually, what I try to say is that your L is here. This is your L. Oh, sorry. 画的不好 ，undo 一下。就这条 L， 哇，这不好画。这条你要找这条 L 的线，实际上就是找 W， 因为这条 L 的线等于 W 嘛，乘上 X 加 B， 但 B 已经不重要了。W 比较重要，因为你最主要是找这个 projection， 那这 projection 当这个 overlap 最小。So the LDA purpose even though we try to find W and B, but in LDA, B is not important. W is the most important because W control rotation of L. So if you find a W, actually you can find a L. But right now L is will shift B along the W. 这条 L 线就是在这条 L 的线，这个 W 在这里，那 L 就是你 W 已经找到了固定角度了，那是 W 这样 shift。那事实上这 W 已经不重要，最主要是找B 已经不重要，因为 B 是这条 W 这样移来移去，最主要是要找 W。因为 W 固定的话，这个斜率就固定了，这 L 的固定了这样子，所以目的是要找 W， 那就是这是 LDA。好 ，So back to here. So our purpose is to find L for discrimination. However, L is controlled by W. So actually, the purpose is try to find W for LDA, linear discrimination analysis, or linear LDF, the same. Okay. So what we do is we base on the equation here, the formulate this one. So we try to find based on the Gaussian model. PCA is a Gaussian model. LDA is also a Gaussian model. So we try to find the mean value, try to find standard deviation value, but we try to maximize this one. So we hope the two distribution, the mean value will be far away as possible. Standard deviation is smaller is better. So after this one, from high dimension to low dimension, the equation become this one. And SB and SW, B is between two classes in high dimension. W is within. Within meaning each variance is as small as possible. Okay, so this is the original sample. We can find the answer. So the purpose is based on this one. We try to find W. So W is the controller rotation of the line. So we try to maximize this one. So we use, what can we do to find W? We use the eigenvector, eigenvalue. So we do singular value, this one, singular value decomposition of SB divided by SW. 我们直接从 SB 跟 SW 这边直接做 SVD， 这不用推导，这已经帮你推导完了。Already derived for you. So the answer is based on SB divided by SW, and this will become your A. Then A do singular value decomposition become UWVT, and then your W, the maximum eigenvalue corresponding the vector, that's your W. This is your answer. So that's LDA. So after you find the W, actually you'll find this projection line. And this projection line, there exists a discrimination line here. And this line can separate two paths as far away as possible. Okay, so the purpose is try to find W. That's LDA. Okay, so next hour we will talk about SVM. We take a break. 那不懂再问我哈，这那个 LDA 的观念是这样子的。我们下课。